The purpose of this video is to review over how to approach both molality and molarity problems as they relate to chemistry. We will start with molality. Molality is defined as the moles of solute per kilogram of solvent. Now, as we look at molality, the first thing that I would like for you to notice is that to solve these problems, the key is just to get your units of moles over units of mass. Specifically, we'll want moles over kilograms. So let's see how we would apply this to a typical chemistry problem. Here we have a molality problem where we have a solution containing 17.1 grams of sucrose, C6H22O11. It is dissolved in 125 grams of water. We are to find the molality of the solution. Now, let's look at how a textbook solution would look for this problem. The textbook would take 17.1 grams of sucrose divided by the 125 grams of water, both stated in the problem. It would multiply that times 1 mole of sucrose over the weight of sucrose from the periodic table. And then it would multiply that times 100 grams over 1 kilogram. Now, this problem does this so that we can convert out of grams of sucrose and into moles of sucrose, and out of grams of water and into kilograms of water. However, just beginning these problems, it may be easier for you to take the problem and break it down into steps. If you do so, we would begin with the 17.1 grams of sucrose. We would multiply that times 1 mole over the weight of sucrose from the periodic table. Grams of sucrose cancel out, and we are now in moles of sucrose. We would take the 125 grams of water that was in the problem, we would divide it by 1,000, and we would convert that over to 0.125 kilograms. Now that we have our moles of sucrose and we have our kilograms of water, we can plug this into our molality problem. So we would take 0.053 moles of sucrose divided by 0.125 kilograms of water, and we would have an answer of 0.4 molality. Here we have a second molality problem. Now in this one we have 3 moles of sodium chloride dissolved in 1.5 kilograms of water. Remember that molality equals moles of solute over mass of solvent in kilograms. 3 moles of sodium chloride divided by 1.5 kilograms of water, and we get a 2 molality for the answer. One last molality problem. What is the molality of a solution in which 25 grams of sodium chloride is dissolved in 2 kilograms of water? Molality equaling moles of solute divided by mass of solvent. Now we have our mass of solvent, and we do have that in kilograms. However, we need to take our 25 grams of sodium chloride and convert this to moles. So we take our 25 grams of sodium chloride times 1 mole of sodium chloride over the weight of sodium chloride from the periodic table. We get 0.4274 moles of sodium chloride. Now we can plug that into this equation. 0.4274 moles of sodium chloride divided by 2 kilograms of water, and we have an answer of 0.2137. Molarity, on the other hand, is defined as the number of moles of solute per liter of solution. So on molarity, our moles will stay the same, but instead of having kilograms, we will have liters. Now let's look at some molarity problems. In this problem, we are asked to find the mass of potassium phosphate required to prepare 4 liters of 1.5 molar solution. We will start with this equation right here. We know that our molarity is 1.5. We know that our liters are 4, and we are solving for moles. When we solve for moles, we end up with 6 moles of potassium phosphate required. However, the problem is asking for mass. So we must do a mole mass conversion. So we will take 6 moles of potassium phosphate times the weight of potassium phosphate over 1 mole of potassium phosphate, and we get our grams. On this problem, what is the volume of a 0.075 molar solution that can be prepared using 90 grams of ammonium chloride? The first thing we must do is take our 90 grams and convert this to moles. So 90 grams times 1 mole over the weight from the periodic table of ammonium chloride, and we get 1.698 moles of ammonium chloride. We're now going to plug that information into this equation. Now we have 0.075 moles, and we now have 1.698 moles here. We're going to solve for our liters. When we solve, we end up with 2.26 liters.